Hello, let me welcome you all on our very first class on bootcamp of artificial intelligence. We had some technical difficulties, so today we are holding this class one more time. And at the first class, I promise that if you fulfill all the tasks, you will learn about basic neural networks. This is quite rare. Normally, it's almost always that people tell about neural networks, but as to recommendation systems, this is quite rare. So this is an interesting part of the course. So I recommend that you get to that and see everything. I'll be giving two first classes on the introduction to the neural networks, where we will simply see what this is and how to train them. And next we will speak about neural networks training, what's the best way to train them, and things that we will discuss during the second class are used in almost all network architectures. The only problem is that we do not still have the necessary basis to apply these methods. So how to apply them you will learn during the third and fourth and subsequent classes. But today we will simply speak about neural networks, and let me introduce myself once again. My name is Grigory Leleitner. I'm today a developer of machine learning in Sberdevices, and there is a title that I have, a senior development engineer. I normally give this a scary title when I work with a more adult audience. I worked also with Skoltech and Yandex, and today I am also a student in the Physical and Mathematical Institute, and my specialization in machine learning is speech recognition, and this is what I do for speech devices in Sber. So let us see what we will learn today, what you will learn to do. So first of all, we will look at today's application of neural networks to make you want to learn it instantly at once, so that you take a lot of effort and make it beneficial for you. Next, we will discuss Perceptron, which is not a very vital model, but it is widely used. And finally, fully connected neural networks. Such networks as such are not really used today, but they are construction blocks for all other neural networks. And also the ways of optimization and finding weights and training these fully connected neural networks can be applied to any neural networks. And finally, we will have some practice where we will learn how to use PyTorch in order to create neural networks, train them, and solve classification tasks. Quite often, such classes start with small demos by Google, accessible by this link. I do not really like them because they are quite entertaining examples, but not too useful in real life. So I've prepared slightly different examples. In fact, these should not be pictures, these should be videos. Unfortunately, I couldn't show the videos, so if you're really interested, you can simply go to YouTube and find these videos by name. The very first one, most interesting application of neural networks which occurred to me is self-driving cars. It sounds a bit strange in Russian. I don't know how they call it in Russian. That's self-driving cars, self-driving vehicles. This is a very vital subject. For instance, Waymo startup is dealing with that, which has been purchased by Google, as far as I remember. So they are developing such cars quite successfully. In fact, the cars which are going to drive by themselves are being developed by Yandex as well, and they are also doing quite well. And in fact, the cars were available for some time in the Innopolis of Skolkovo. You could order a taxi and get a car with a driver sitting in the front seat and having his hands on the wheel. But in fact, the car was driving of itself, and the driver is only necessary in order to comply with law. Still another application of neural networks, that's what I do. That's voice recognition, speech recognition systems and interfaces. This is something which allows eliminating a certain barrier in communication with electronic devices. And I am dealing with a part of speech recognition so that the machine understood what you say. There is a dialogue part and speech synthesis so that the machine understood what exactly it was that you said and give you an answer in some sort of human voice. I think this is another interesting and highly prospective example of applying machine learning, which will bring a lot of money to companies in the future. Still another interesting thing is GitHub Copilot. You might have seen it somewhere in Vkontakte network or social media. People admire this neural network, how it works. So some comments describe what this network does, then give the name and a signature, and the code itself is generated by the network. It seems magnificent. This is something which allows replacing programmers in the future, and they cost a lot, but the programmers believe that this network will not replace them, but will simply make their work easier. And still another example of application which is mostly interesting for me. This is a game which uses artificial intelligence. It is very similar to Dungeons and Dragons, if you ever played it. So if you didn't, let me try to explain. Neural network generates some world after which you can enter in a text way what you want to do, how you want to interact with the world, and then the neural network will generate the answers of the world to your actions. For instance, you write, I want to go to the forest. And the neural network generates that you are attacked by robbers and how you're going to communicate to them. But there is a downside too. If you play it long enough, you'll understand that the neural network does not truly understand what you write, and mostly and rather generates the text in a similar way. So those powerful language models which are a property of the neural networks, do they really understand the language? This is still an open question. Some people say yes, some people say no, but we do not know yet. Okay, so now you're super motivated to go through the entire course to the end. There must be a boring part to it where I tell about the history of neural networks. It may be boring for me, but normally this is something people tell about during academic courses. I don't really want to, because our course is an academic one. We could go through all this timeline, but let me tell you the main part. Artificial intelligence already had two so-called winters, where investments in artificial intelligence ended. People decided that there is no more prospect to it anymore, and they stopped investing in it. But currently, we have revived from the second winter, and today a lot of investments are made in artificial intelligence and neural networks, and people have very high expectations from that. Nobody knows what comes in the future, and whether neural networks will justify those hopes. I believe so, because they already find some commercially successful applications and uses, so they may develop endlessly. still we will have some history, because this Perceptron model, neuron model, comes from history. As far as I know, at the moment, nobody uses it, because there is no point in doing it. In a way, it is very similar to what logistic regression is made, how logistic regression is made, and this is something people do use. So let me tell you what it is and why is it called a neuron model. So what do we call a model at all? We will call a model some kind of description or rule where from the incoming properties we receive an answer. In this case, the perceptron works as follows. We take the total of all the incoming figures and then add W0 and apply the activation function to this. The activation function is drawn as a sort of a step. And why is it a neuron model? Well, in fact, it is very similar to how neurons work in our head. They have axons which connect them to other neurons, and that way they can receive a pulse, an impulse from them. Those axons have different extent of conductivity. That is how receiving a pulse from a different neuron affects that other neuron. So there is the intensity of a pulse and the conductivity. All that is added together because we have different sensitivity in different axons, and if this total exceeds a certain limit of potential, then our neuron gets activated and sends a pulse to all those which are connected with it. So neurons in our brain, as far as I can tell, I'm not a biologist at all, to be honest with you, but it seems very similar to how our neuron model is built, with some difference that these are much more complicated. And the main difference is why neural networks, artificial neural networks, which we train and which are made as zeros and ones in the computer, why can't they be compared with brain? The thing is, neurons in our head are not organized in layers, but in much more complicated manner. So complicated it is we cannot even assume what is the organization that we got in our head. So you should never say that neural networks are similar, biological ones and artificial ones. Most likely people will not understand it, so you shouldn't do it. So another interesting point about Perceptron, that is how we teach it, how we train it. I just told you what Perceptron model is and what is the rule which allows us to receive an output from the input. But we believed that we got some weights from above, but this is not the real picture. We must receive the weights somehow. We receive them through the training algorithm from some data which we already got. So we have some data to which we already know the answers, and that way we try to understand what are the weights which describe them best. So we use this algorithm. You don't have to go deep into it too much. I will not tell about it, but the thing which I want you to understand is that it is iterative. So we make some updates to our weights until we decide that we're good and we already got good weights. Here again, we must have a video with how our perceptron gets trained. If you look at the left rectangular, there is a line which is a dividing surface of our perceptron. So everything above it we classify as red dots, or let's say class 1, and everything below it is class 1 green dots. So it's important to see that this division line is straight because Perceptron allows linear classification, and that's the downside of Perceptron. Let me explain why. We have just 4 points in our training dataset. Would they be positioned as in the first picture? Let's say dots are class 0 and star is class 1. And if they're positioned that way, Perceptron can do it easily. We can match our weights to classify this picture perfectly. And if they are positioned the way the second picture shows, then the weights can be matched easily. But if we look at the third picture, we cannot match the weights so that Perceptron could classify them well. It seems that it is quite clear. We got 4 points, but we cannot draw the line so that we had 0 class on one side and 1 class on the other side. Why is it a problem at all? The point is that real data is made in a very complex way, much more complex than these things. If we cannot find weights which make these dots positioned in a perfect way, that means this model is not suitable for other tasks either. People thought that neural model allows us to make models of animals or making mechanical helpers. But finally people got disappointed and understood that this cannot be done with the Perceptron. In fact, this problem was a significant reason which caused the first or the second winter in artificial intelligence, which cut investments. On the other hand, when this problem was discovered, a solution was found. What if we use not just one neuron, but layers of neurons, where each neuron in some layer will be connected with all the previous neurons? And it is clear why this is called layers. Now let us go through this and see how we get our outgoing value from this model, so that you understood what this chart means at all. So let's imagine we got some weights. I've recorded them randomly just to get some nice values. So let us now calculate what will be the total for the first neuron from the second layer. This second layer on the right or on the left, it makes no difference. So we multiply 1 by 1, we multiply 2 by 3, and 1 by 1. We add all that together and we get 8. We do the same with the second neuron. 1 by minus 2. We finally get 5. And now we must apply activation function for these neurons. The activation function for us is a step. We had 8 and we got 1. We had minus 5 and we got 0. So it's all logical. So how do we get the output? We multiply 1 by 2, 0 by minus 1, and 1 by 1. So we get 3. We apply activation function and we get 1. Cool. And I hope you believe me if I tell you that this model, which is a little bigger with slightly more neurons in the middle, easily solves the XOR problem. And in fact, these are excellent models which are multi-layer neural networks, the predecessors of today's models. So why do you go back in my slides? The thing is that it's very important to see that, in fact, computation of the values put in these neurons can be recorded with linear algebra. So why is it important? The thing is that we know very well how to work with linear algebra, especially with the operations including matrices. So when we record receiving the values in such matrix way, that means that we can apply different optimizations which people invented a long time before us. So receiving the value of the subsequent layer from the previous one looks as follows. We multiply the vector of inputs, 1 and 2 in this case, by the matrix of weights, which is 1, 3, minus 2, 0. Then we add bias, so that's the constant, and here is 1 and minus 3, and apply activation function. And the activation function, in this case it's f, is the vary function which will work on vectors, and we will apply it element by element. And in fact, the majority of activation functions are made so that they work separately with each number. So if we applied it to a matrix, we would simply get each number through these activation functions. So there are activation functions which work with more than one number. I'll tell about those later. Okay, so our fully connected layer, the rule by which we receive the value of the subsequent layer and the value of the previous layer is recorded as follows. Li plus 1 is the vector of activation of subsequent layer. This is the activation function taken from a matrix multiplication of weights with the previous layer's value and with bias added to it. So now, why do I call activation function and not a step, the way we had it in Perceptron? The point is, if we use a step for activation, we will not be able to find weights well for such kind of neural networks, because the algorithm, which I will tell you about a little later, which allows finding weights, works for differential functions, and a step is not a differential function. But if we take instead of it anything from this list, then everything will be excellent. So let us now speak about activation functions. What can they be? First of all, it can be step. Non-differential, it's bad, it's not used in neural networks. Linear activation functions, what does it mean? It means we do nothing with our output at all. We receive a vector and we give it further. So, a question, checking your attention. Why can't we use linear function of activation in every layer? What will happen? When we add to our neural networks some new layers, we want it to become better. And if we have two layers, one after another, and a linear activation function between them, then the output of the second one would be a linear combination of linear combinations. So that is a linear combination itself. You have two layers with linear activation function between them is the same as having just one layer. And clearly, it's very strange to add layers when it does not allow your model to be better. So the linear activation function is not used inside the network. Most often we will use it at the end of the neural networks when we want to predict some value, some number minus or plus infinity, or when we need logits. I'll tell about those later. Next, activation functions are similar, but they're different. First of all, it's a sigmoid and it's a hyperbolic tangent. If you look at them, they are slightly have S shape. This is why sigmoid is called sigmoid. Its property is that it transforms any number into a number from 0 to 1, and a tangent transforms from minus 1 to 1. So if we extend it, it does not, if we extend the sigmoid, it does not fully coincide with a hyperbolic tangent. But previously, when they were used inside the neural networks, there was no difference between them, in fact. Today they are not used so. I'll tell you why. We use sigmoid when we want to receive some number similar to probability, and let's say logistic regression, the output is one number. We need to make a binary classification, and one number is the probability of belonging to the first class. So for the output, we apply sigmoid. The next activation function is very interesting. It's called Softmax. This is the activation function applied, which is not applied to every number separately. It takes all the output of the layer and transforms it somehow. It cannot be separated, every action by every number. So you can see the formula, how it's calculated. We simply take an exponent and put it in the extent of these numbers which we received and transform them so that the total was 1. So why is softmax used? That's when we want to predict the distribution of probabilities. Let's give an example. Let's say we want to classify dogs into different breeds. Let's say we have 15 breeds. So at the end, we want to receive the distribution of probability. So at the end, we will have 15 output neurons with the values minus infinity plus infinity and the total of the previous outputs. And those numbers, minus infinity plus infinity, we will apply a softmax to them in order to receive some distribution of probability. Let me mention here that in PyTorch, I'll mention it again during the workshop, but I want to say this now as well. So when you make a multi-class classification in PyTorch, you lose loss, cross-centric loss. You don't need to apply softmax at the end. I will tell about this later. I simply want to focus attention on that. Some loss functions, even if they assume that your outputs are simply probabilities, but you need to apply, you need to submit what you had before softmax. I hope you remember it. And finally, activation functions, that's a working horse of all neural networks today. That's ReLU. It's very popular, used as activation between layers, non-linear ones, because if we had a linear function, then two layers could be turned into one. ReLU is added between the layers. This is easy to calculate, so it's got very good values, and it is most frequently used for our neural networks. So we have learned about the model, and now we have to see how to find weights, which is actually quite difficult for neural networks. So now let us see what we want to optimize. Same as for all the machine learning, we have some function of losses, that is loss. I will most frequently say loss because the function of losses sounds longer. I hope this English word will not confuse you. So let's say we have to predict some real number, some value, let's say a price of an apartment or a price of a car, something like that. So in order to receive our losses function, we will add the square of differences between the real value and the one that we've predicted. So to find our weights now, we need to minimize this losses function and find such set of weights and numbers which we put instead of weights, that the value of losses function would be minimal. So how do we do it? Fortunately, we have the gradient descent. In fact, there is many more methods, but it turned out that the gradient descent works perfectly for neural networks. So what is it? It allows minimization of absolutely all convex functions. I hope you know what is a convex function from the course of math. For instance, we have square, so we need to find the minimum of this function, or a point where the minimum is achieved. So how do we do it? Let us initialize our x. Let's say we got 4.35, and then we will find a derivative of our function. The derivative of x squared is 2x, and in 4.35 we will get 8.7. So this means if we increase very slightly our x value, then the value of the function will increase. And if we decrease our x value, the value of the function will decrease. That way we understand we have to go left. And we can make a small step, look at the derivative again, and that way get to our minimum. This picture is not very fair. It may turn out that at the very bottom we will go through 0 and get to the negative x area, but then our derivatives become negative as well, and then we'll understand that if we make a step to the right we will reduce our function. So we make this step, and after some time, if we make really small steps, we get to 0. Now let us try to formalize this in a formula. So we initialize our x0, and then at every step, itinerary algorithm, we take from the previous xt, we deduct derivative f in this point, multiplied by some alpha. Alpha is simply a constant which we assign in advance, a small value, a small number. This is a simple function. We can use an analytic derivative. So xt plus 1 is equals 1 minus 2 alpha xt. So if this is some number which by its module is smaller than 1, then after some number of steps we will get to it. But if it's more than 1, we will go apart by a module. We will make bigger and bigger steps. That way we understand that this alpha should be chosen as some quite small number. We will call alpha a learning rate. It is quite hard to choose a learning rate. We don't know how to do it, but somehow we manage doing it in neural networks. So let's now generalize this for neural networks. In neural networks, W best would be some set of weights. This is not one matrix, because in neural networks, matrices can be of different size with different vectors used for weights. So W best is simply a set. I am probably not using the mathematical notation quite right, but let's say these are our best weights which we want to find, and they minimize the losses function. Then we will take gradient instead of the derivative, and gradient is a vector. It shows in space. Let's say if we drew a graph of a losses function from weights, then the gradient would be some vector. Possibly, well, here there is a visualization for cases when we only have 2 weights, whilst in fact there are normally millions of weights. Unfortunately, we cannot build a million-dimension graph, so we have to think of this intuition. So we make we take some direction and make a small step against the gradient, and we get this formula for the step of weights updating. Such way of updating of weights is called gradient descent. And as I told you, it works very well. It is supposed to get to the learning rate only for convex functions. And if our function is not convex, however small number we take at the beginning, there is no guarantee that we get the minimum. Or we can go to some local minimum or go down endlessly if we don't have a minimum point. So we get to some strange picture. On the one hand, we found the way to optimize finding the weights, but on the other hand, it doesn't give us the argmin. That is, we do not receive the weights which give the global minimum of the losses function. So it turns out that not even global minimums, but the weights that give us local minimums of losses function are also quite good and are used everywhere. Okay, so now I understood that we need to receive the gradient of losses function by weights, that is vectors from derivatives of losses function for every particular weight. So how do we get that? We have a very interesting method which I will tell you about. But first, intuition. You see, we have a very simple function of x plus y multiplied by z, or we drew it as a calculation graph. Why? Because neural networks are also presented the same way. In fact, a neural network, if you remember, is a composition of layers, every layer being a function, and the composition of such layers is a neural network. So how do we calculate a derivative here and transfer this intuition or translate this intuition into neural networks? Let us introduce another value. Let's say q would equal x plus y, and start calculating derivatives. df pdf pdz is all clear. Sorry, I made a mistake here. df pdz is 3, df pdq is -4, and now we get the magic. Indeed, we wanted to get df pdx and df pdy, but we received a df pdq for some reason. Why? The thing is, we got some such a thing as chain rule. This is a derivative of complex function. So if we want to calculate df pdy, we can calculate df pdq and df pdx, and then calculate the number. The same can be done for df pdx. So we can take df pdx, we calculate df pdq, dq pdx, and we're fine. So with the help of this calculation graph, we found the derivatives we want. Once again, let's look at how these derivatives were calculated. Let's imagine that f is some kind of operation, maybe an operation inside the neural networks with the inputs of x and y and output as z, and it also has some local gradient it knows about, dz pdx and dz pdy. So calculating the derivative of output by the input is quite easy. Our function must be able to do it. From the outside somewhere, we receive a gradient, a derivative, the pdz, the function of losses from our output. So what do we do now? We calculate dl pdx with the help of theorem of complex function derivative. So dz/pdx is a local gradient which we know how to calculate. Hooray! So dl/pdx we can give back. We have calculated this gradient, and the same can be done with dl/pdy. And now imagine, in fact, f was a matrix multiplication, and x is the output of the previous layer, and y is our weights. Thus we have found dl/pdy, a gradient of our losses function by the weights, and dl/pdx is the gradient which we will pass to the previous layer so that it could also calculate its own derivatives of losses by its weights and by its inputs and pass it further. This is a small illustration of how these graphs what these graphs look like in neural networks. I do not remember what kind of architecture this is exactly. Probably Google NiliNet, but I'm not sure. As you see, it consists of these kind of operations. You cannot see arrows from the weights here. This is simply these kind of illustrations, but in fact every rectangular includes not only a blue arrow which signifies outputs of the previous layer, but also another arrow which signifies weights. And we could calculate our gradients with the use of this rule. In fact, I lied a little bit here to simplify our narration. The point is that Z actually is a vector or a matrix or something else even higher dimensional, let's say a tensor, a matrix with 3 dimensions. And it is not very good to record derivatives for it in such way as dl/pd z dl/pdx, because we can multiply numbers like that. But if we start multiplying matrices like that, or tensors with 3 dimensions, we have to mention what this multiplication actually means. But most likely the biggest you will have to deal with is matrices, so for them it will be matrices multiplication and things will be fine. But if you want to figure out how this algorithm really works, you can Google Backprop and check it in more detail. Why is it called Backprop? This is still another video which was supposed to illustrate why is it called Backprop. Because we have two ways to pass our network, through our layers. One is from the left to the right, from ingress to egress. So we calculate our prediction. Then we go from the right to the left when we calculate our gradients. So first we calculate the derivative function of losses by the outputs of the last layer, and then of the last but one layer, and then the algorithm which I just showed you by these illustrations. So the pass from left to right is forward pass, and from right to left is backward pass, and the entire algorithm is called back propagation because we sort of push the gradients backward. Fine, so we have learned how to receive good weights for our neural network. So we take a gradient, we get a back propagation, and we have gradients which we can use for gradient descent to minimize our losses function. It's all fine, except for one thing. Normally our datasets have sizes of millions, and it's very hard to get trained on them because we need all these computations which I just spoke about must be done to matrices with one of dimensions of a million, or could be tensors, or could be pictures 300 by 300 or 400 by 400, and computations become too numerous, too bulky. So what can be done? Let us look at our losses function. It's a total of the losses functions of every example of training dataset that is on some standalone objects. So then the derivative of losses function on anything will equal the total of derivatives of those d-lits and d with a star. So what can be done here? We can take this long computation, or we can take a different way. We can only calculate some randomly selected elements from our dataset, and with this sampling, with receiving this sub-sampling from our training sampling, we will approximate, we will come closer to the real gradient at every step of the gradient descent, and we will step forward that way. So what will it look like finally? Let's again imagine a million-dimensional space, and as an illustration we have these figures. We have x, y, that is two parameters of neural networks, two weights, and these lines signify isol lines of losses functions. These are the lines where there is just one value of losses function. So if we follow the usual descent, we make these small steps to the local minimum which we will have found somehow. But if we make stochastic gradient descent with a small batch, then our gradient becomes more noisy. It becomes more random. So we do not really go to the very bottom directly, but we sort of go in loops. But the more we work on our gradient, the less loops we have. Good. Once again, I cheated you a little bit. I do that a lot during this lecture. The point is, we do not simply choose random elements from our dataset at every step. Then it would be that on some of the examples from the training dataset, we get trained much more often than on others. Why do that? Well, it's good to make them random, but we can do the same in a non-random way. We can get our dataset and mix it and split it into pieces of batch size. Let's say k size, which we wanted to select randomly, and then go successively in succession along these pieces or batches, and one go through these pieces we will call epoch. And it's very convenient that with a certain number of epochs we can measure the amount of training which we have received on our neural network. And these bits, these pieces, it is written here many times, into which we break the data set, we will call them batches. The gradient descent, a mini batch gradient descent. For mini stochastic, there is no big difference anymore. Stochastic gradient descent or mini batch is when we calculate the gradient not by the entire dataset but by the batches, and the size we will not call k anymore, we will call it batch size. So this is simply the name for the derivative. So why do we need to mix the dataset, you may want to ask. The point is, by its nature, dataset can come already sorted. Let's say we got a classification for three classes. First we have class 0, then class 1, then class 2. So we split them into batches, and we get every batch with elements from just one class. Then our approximation of gradient, in fact, will be very, very bad, because the real data set has equal number of every classes, and in our batch we only got one class. This is why approximation will be bad and we will get nowhere. Okay, now let's move. We are getting closer and closer to practice. So what frameworks do we have for neural networks? There is mainly Overflow and PyTorch. There are others, but I never use them. Maybe Learn, but it's not usable for neural networks, and ONNX is simply used for transferring models into different executable media. So let us choose between Overflow and PyTorch. So why is PyTorch good? It's got the code style which is very similar to Python. There is also PyTorch Lighting, which is a very good library or repository, which allows you to get less of low-level details. It's got support of mobile devices. TensorFlow became very similar to PyTorch, especially with the second version. It's got Keras, which is something similar to PyTorch Lighting. It's got a lower level API, but finally it is harder to debug it, and I simply like it less for development. So our today's practice will be on PyTorch. Okay, so the lecture comes to the end and we are coming to practice, and let us repeat what we have learned today. So first, we have learned what is Perceptron, how it is made, how it is optimized. We have learned how fully connected neural networks are made, how to optimize them, namely using gradient descent, and that is done by backpropagation. And what are the differences between TensorFlow and PyTorch, and what we will choose? PyTorch for our practice. So follow this link in Colab, copy it to your laptop, and we will make a small break for several minutes and then come back and start our practice for 3 minutes or so. Okay, fine. I think our break comes to the end, so let us start our practical part. We have a very practical course, so we will start training our neural networks, and I will show you what is happening and what is every bit of a code which I am executing. Yes, I wrote it myself. So what are we going to do? We will write the neural network, we will train it and look at the computation graph. A small spoiler at the very start. If we go down and look at the code which we will write now, this is what we are going to have today. You can see even some comment here in the middle. Quite a small amount of code, but I hope that my explanations will help you to understand what it does and how it can be used. Okay, so let us start with data. Every task in machine learning starts with data. It's a lot of fun to play with models, but without good data you get nothing. So let's see what we got from a scalar. I assume everyone's familiar with a scalar and what is a trend as speed. This is a special function in scalar datasets which simply generates occasional points, random points which look like this. Here is a small spoiler again. Okay, so we'll look at this cell and see what we got from here. This is a simple massive. First dimension is samples and another one is properties, because our examples in the training dataset are dots in a two-dimension layer. So these datasets, according to PyTorch, is any object which has underscore and underscore len. So this is an object from which we can ask len, and through the square brackets we can ask some tenth or any element. In fact, the X-train already suits all these properties. Look at this. I make it X underscore train. It's got length, and apart from length we can get some element, let's say 10th element. Let's say we get the 10th example from the data set. But the point is that our data set does not only consist of properties which we received, but apart from properties we also need labels. So we want that when we write like this for our object returned as tuple, where the first element will be one of these properties and the second element would be some number, either 0 or 1, first class or 0th class. So we will now use a class available in PyTorch which works with tensors. Tensors are approximately the same as massives in NumPy. They are simply structured differently and are a part of PyTorch. So if we to receive tensors from NumPy massives, we will call the function torch.fromNumPy, and if we put out our X-train again, we will see this comment tensor, which means that this is a PyTorch tensor. We use the class which I spoke about, and where I imported it from, you can look above. So we transfer X-train, Y-train, and we get an object which has those two important properties. We can check the length and we can take certain element. this element gives us what we want. This is a tuple where the first element is the properties vector and the second element is a number or class. Good. So why do we even want to do it? Because we need data sets in order to do data loader. A data loader is a special class in PyTorch which cuts the set into batches for us. All is left for us to do is to make this object and pass the data set as the first element and pass the batch size we want as the second element. So in this case it's 10, and then shuffle. You can see that I am shuffling the training dataset, but I'm not shuffling the validation one, simply because in the validation dataset the order plays no role. So let's look at this object. Train dataset, train data loader, not too much information here. So this will give us an object which will be an iterator on our batches. If you do not, well, actually all you need to know is when we call next iter, we will get the very first batch. So then we can split this batch into properties and labels and put them separately. So we get the properties here. This is a matrix of the height 10 and of the width 2. That is, we have 10 examples with 2 properties, and the labels are simply a vector of 10 elements, zeros and ones. Okay, so now I think it's clear more or less what is Tensor, how to work with the data loaders and datasets. Now we go to the neural network. PyTorch is convenient for already having classes for the layers of neural networks and integrated auto gradient. That is, you will not have to write all this nightmare for the computation of gradients, which we spoke about before. Okay, one interesting question is, how many layers does this neural network has? It seems 5, because it's got 5 rows of these blue dots. In fact, there are 4 layers, because each layer is the set of these weights, the set of these connections. Just a question for you to remain focused. Now let us look at the PyTorch layers. To do that, we will create an artificial batch of 3 elements to feed it to our layers. In order to create an object of a layer, we simply take this linear layer. It assumes 2 mandatory arguments. The first one is the input size, and the other one is the output size or dimension. So this linear layer will calculate that at the as the input data it will have 2 properties, and as the output data it will give 4 properties. And the next is ReLU. ReLU has no parameters because it's a very simple function which takes maximum of 0 and value. Let's assume our semi-connected layer to batch X. This is all clear. We get the output of fully connected layer, and we got all the negative numbers zeroed. It so happened because that's how we created the layer, and the weights get initiated somehow randomly. So it so happened that we got negative values for weights, and they all zeroed for ReLU. So how do we create our model? It is quite simple. So it consecutively applies layers already existing in PyTorch. To do that, an end sequential is used, and we simply transfer all the layers we want to apply to our data in the order we want to apply them, and we are given one object which will be our model. We can apply it to the data same way as we did before with the layers. Excellent, you got a model, and now we have to define the losses function. Take another look at the model. We have binary classification, and we predict two numbers. This means that for the output we will not use sigmoid, we will use softmax, but when we use this particular loss, cross entropy loss, in PyTorch it is a little bit tangled. You have to give it the last linear layer without softmax, because the softmax is inbuilt in this cross entropy loss. So how is calculation of losses function made in it? You pass the output of the last linear layer which you received from your model. You can see that your last layer is linear 1, although we could actually write it like this. If our loss worked differently. For instance, if you make neural networks in Tensorflow, this is how you must do. But this one is not Tensorflow, it's a little bit complex. Softmax is already inside cross entropy. Good. So now let's see how we apply this. Again, this is an object which we can get from predictions as the first argument, and from y's as the second argument. So let us get random predictions and apply our criterion losses function to predictions, and as an answer we receive one number, tensor, and there is a reference to the operation which created it. These are the references, the links with which the computation graphs work, which we will discuss later and which we saw before in the lecture. Still, another interesting part is that for losses, when you make an object, you can pass reduction equals none. What it means, normally the reduction is mean, which means that the losses are averaged for the whole batch, whilst if you put it none, then the losses function will give you vectors without any errors for each element. For instance, we had 3 examples. We got the vector of 3 errors for each of these examples. This gradfan allows making backward propagation. Let's see how it works. Once again, we calculate loss, and now let us look at the gradients. Where are they stored in PyTorch? What is model.parameters? Model.parameters returns you the iterator by the model parameter. When you put next of iterator, you receive the very first model parameter. Most likely this would be some matrix from the linear layer, and this very first parameter, with this we can check dot grad. With tensors, that's where a gradient is stored, and before we called backward it said none, but after we called backward we got full-fledged gradient. Hooray. One more thing to mention, gradient can be added each time you call backward. Well, now we have made the same predictions and once again called backward, and you can see that all the values of the gradient are doubled. How does that happen? When you try to calculate the gradient for the second time, if PyTorch sees that there is something under dot grad, it simply adds a new gradient to what was stored there before. So if you've missed a batch, for instance, and you calculated gradients and updated the weights and then did not zero gradients, then at the next step the new gradients will add to the old ones, and your optimization will break because it will not be clear anymore which direction you're going. So it's very important to update the gradients. Let's see how this is done. That's done with optimizers. That's another object in Python. In order to create an optimizer, we give it as arguments the iterator of parameters. Parameters are special tensors available in the model and marked so that they must be optimized. After that, we submit our learning rate, that is the size of steps we're going to make. Cool. So we got everything we need for training our model. We got data, we got the model itself, we got the losses function and optimizer. The only thing left is to write the cycle in which it will happen. For some reason it has been launched already, although I never even touched it. So what kind of cycle is it? Stop. We will iterate here by epochs. And in every epoch, we will iterate in a train data loader. So first we will zero the gradient, then calculate the output of our model, calculate the losses function, make a backward pass. Now we got the gradients for our parameters. We call optimizer.step, and then when we make it, it goes through all parameters of our model again and updates all the weights, checking the gradient. That is the content part. All the rest of the code is necessary because, first of all, we put here all our losses on the batches in order to make a nice graph after all. And for every 5,000 iterations, we put in what accuracy we received on the current batches. Accuracy actually is translated as being precise, but it doesn't sound too good in Russian because we got two different matrices, accuracy and precision. That's translated as one word in Russian. So here I'm using the English word accuracy. Okay, so we have collected everything, and let's put it all together and try to train our model. We take the data, we take the model, we take the losses function, we take the optimizer, and our for in which we step along the dataset and update the weights. This is what our model looks like, and now let's see what the losses function looks like. As you can see, it is decreasing, which is very good. That means our model is learning. It is also important to mention how we understand that our model has trained. How long does it take for it to get trained? Let us try to put a little more epochs. Let's say 200. And put out our losses function. You must end your training when you see that with 1 or 2 epochs or more, losses has not fallen, which means that your model has achieved its limit, and if you continue training it, nothing will happen most likely. You can see we can probably train our model more and it'll become even better. Now let us visualize what we got. While it seems the classification is quite good, the red area of our model is classified as things belonging to 0 class, and the bluer are those more likely belonging to the 0 class. We are running out of time, so it's better if you read the remaining part of the notebook yourself. It's got a lot of clarifications, and we will round up and you can ask questions. So what have we done today? First of all, we have learned how to work with the neural networks, fully connected neural networks in PyTorch. We have learned how to create them, how to train them, and solve classification tasks, and solve them quite well. We've found out what neural networks training consists of, and we've learned how gradient and PyTorch works, what are computation graphs. You will learn that actually if you read everything written here. So what happens next? During the next class. Next, I'll tell you how to train a video card, what are the elements of gradient descent, what is batch norm, and what is dropout. All these things are extremely useful, and if you are going to continue working with the neural networks, you cannot live without those. These are the very first things which you must learn. That's it. Thank you. I got a few questions. Let me answer them. Batch goes back and forth between the layers. I am not quite clear. Well, I probably understand what caused this question. Let me explain this once again. Look here. Here is my neural network graph. Batch is simply a subset of data from our training dataset. This subset is very good to present as a matrix, where the first dimension is the batch size and the second dimension is the number of properties. Why is it convenient to show it as a matrix? Because inside the neural networks there is a lot of linear algebra, so it's very convenient to multiply it. So look, let's look at the neural network training code. Here we send the data of our batch left to right when we go from inputs to outputs in order to receive a prediction. Here, when we make loss dot backward, loss basically is the very last top in the computation graph. This is something we receive at the end. So now we look at the dot backward. This means go back and calculate the gradients. So it's hard to say that a batch goes back. It's more that we go back along the neural network from the last layers to the first ones and calculate the gradient. If you get any more questions, please ask them, and this is the time when I answer them. With the AMD card, can we train models? As far as I know, yes. If you try really hard, there are some libraries or repositories which support training of neural networks with ATMD video cards. But the problem is most popular frameworks are not designed for that. PyTorch and Tensorflow, as far as I know, rely a lot on the library called QDNN, Q Deep Neural Networks. A lot of things are implemented in there necessary for neural networks, and the maintainers, those who develop frameworks, do not want to write it themselves. This is a very complex code for computation of different operations. So as far as I know, for AMD, I may be wrong, but there is no such good and big library or repository. So consequently, no big frameworks which might support training on AMD. A connection of GPU on PyTorch, is it the same as on Payflow? So how do you use GPU? If you work in Google Colab, then you don't need to do anything. You have Qdo and QDNN installed, the libraries which enable frameworks connecting with the video card. At the next class, I will show it at the very beginning how to transfer the computations from the processor to the video card to make things much faster. It simply takes adding just two lines. So in a way, yes, connection is the same. If you work on your own laptop, on your own PC. First, you have to check whether Kudo supports your video card. You must install Kudo, you must install QDNN, and then PyTorch and or FineFlow supporting Kudo, and things will work. Somewhat in 2016, it was very hard to install Kudo on Linux, but today this is done easily, and most likely you will have no problems at all if you follow the tutorial. Before, things were quite bad with that. I got just central processor Intel i5 of 11th generation. Well, probably the processor, because with integrated video card you won't be able to launch all these computations, because most likely it will not support Kudo. It is possible that Intel has done something and a part of computations may go to the integrated graphical processor. I do not know. This is quite a difficult thing. I only worked with the GPU and video cards because processors are slow, and TPU are special analogs, somewhat similar to video cards but more specialized for training neural networks from Google. You can receive them in the Google Colab. You can select here execution environment, and here you can check GPU or TPU, what you want. Or in the Google Cloud you can use TPU. How many epochs approximately does it take to get the neural network well trained? Well, it depends on your neural network, on your learning rate, on many things. The only thing you can do is look at the graph of losses function, and if it has not decreased a long time and it's clear that it is not going to decrease anymore, then you can believe that your neural network has trained enough. There are millions of parameters, and it's very hard to say anything precisely about such functions, but as soon as it stopped getting better, you can decide that it's done. It seems that we ran out of questions. I thank everyone for attending our class and for pumping your skills in neural networks. I hope that you'll be interested in this course and it will be very useful for you, and you will then go and work with the neural networks, because the more people doing that we got, the faster we will create artificial intelligence and relax and get machines working for us.